In this video, we're going to discuss the synthesis of carboxylic acid derivatives from carboxylic acids. So first up, we're going to discuss the synthesis of acyl chlorides. This is going to bring us some familiar reactions. We've actually seen these before. If you react a carboxylic acid with thionyl chloride, it does the same thing that we've seen with alcohols. It's going to replace that hydroxyl group with a chloride. So this would give us an acyl chloride plus sulfur dioxide plus hydrochloric acid. Remember that when you're doing this type of reaction, these are just byproducts that I'm giving to you so we have a balanced equation. It is just the organic portion that we're really concerned about here. In the next reaction, we see phosphorus trichloride reacted with 3 equivalents of a carboxylic acid. This is going to give us 3 equivalents of an acyl chloride. Plus phosphorus acid. The next one shows a carboxylic acid reacting with phosphorus pentachloride. This is going to do the same thing. This is going to give us an acyl chloride plus POCl3 plus hydrochloric acid. The synthesis of carboxylic acid anhydrides is a little newer to us, but it's fairly simple. The carboxylic acid anhydride can be looked at in 2 different ways. You can look at it as 2 carboxylic acids that have been joined together that now share a common oxygen, or you can look at it as a substitution of a carboxylate onto another carbonyl. So this first synthesis looks at it in the second way. We look at our carboxylic acid and we have our acyl chloride. Now remembering that the acyl chloride is the most reactive and chlorine is a very good leaving group, what we are going to see is that the carboxylic acid is going to be deprotonated by the pyridine, that's why it's there, so that it ends up giving us a carboxylate, which can then act as a nucleophile to attack the acyl chloride. And then we'll eventually push out the chlorine. So what we end up with is the carboxylate substituting onto the acyl chloride. Sorry, I switched my color coding. This is in orange, and this is in blue in the product. Another way we could look at it is the first way that I mentioned, where we could look at it as 2 carboxylic acids coming together and now sharing a common oxygen. This occurs through a dehydration mechanism. It's not really one that we've seen before. This is essentially going to involve substituting one carboxylic acid with the other. And this is accomplished by heating. It can also be accomplished by adding in a drying reagent. So this is going to create a cyclic anhydride. This specific one is succinic anhydride because it comes from succinic acid. Our next one is a really big topic in this chapter. This is the process of creating an ester from a carboxylic acid. This process is called Fischer sterification, so it is a named reaction. It has a really nice mechanism, so we're actually going to look at the mechanism on the next slide. But in Fischer sterification, your carboxylic acid is substituted by an alcohol. The reaction conditions are an excess of alcohol in acid, and it is reversible in aqueous acid. These conditions should remind you so much of something from the last chapter. Do you recognize it? What do we get if we react a ketone in the same conditions? An excess of alcohol in the presence of a strong acid. The answer here would be an acetal. But if you're doing this reaction with a carboxylic acid, you don't end up with an acetal. You end up with an ester. And this is again because of that whole leaving group concept. So we end up with the acyl portion of our carboxylic acid, and the alkoxide portion of our alcohol turns it into an ester. And again, this is reversible. If you take this ester and put it into aqueous acid, you'll get your carboxylic acid and your alcohol back. The byproduct of Fischer sterification is water. So ultimately, this is a condensation reaction. So let's take a look at this mechanism, only because I like it so much. So we have our carboxylic acid, and we are in acidic conditions. Remember, we're going to go forward in this, so we're not going to worry about the H3O plus right now. It's not there. We're only looking at the theoretically strong acid and our alcohol and our carboxylic acid. So the first step of any mechanism in acid when you're using carbonyls is to go ahead and protonate the carbonyl oxygen. This is going to make the carbonyl carbon much more electrophilic. Hopefully you recall that handy resonance structure that we looked at with aldehydes and ketones. When you protonate that carbonyl, you put a positive charge on the carbonyl oxygen, but you have a resonance form that shows the positive charge on the carbon. And this helps us to see what our next step of the reaction is going to be. Our next step is going to involve the alcohol attacking the carbonyl carbon. This brings us to our tetrahedral intermediate. Now, at this point in a mechanism with an aldehyde or ketone, we would deprotonate at our positive charge and call it a day. But if we do that here, we're going to end up with 3 oxygens all attached to a central carbon. And if you're thinking, well, that's something I haven't seen before, you're right. It's not something you've seen before, and that's because it's not going to be very stable. Having 3 electronegative atoms attached to the carbon is not going to work out well. So instead, we're going to deprotonate the alcohol using another equivalent of alcohol, because there's plenty of it around. And then we're going to kick out one of the hydroxyl groups. So looking at this, you should recognize that having those 3 oxygens on there is not the best idea. So we're going to pick up a hydrogen and turn the hydroxyl group into a better leaving group. So now that we've protonated it, it is able to leave on its own. Which brings us to this carbocation, which has a resonance form that helps to stabilize it. And this resonance form probably looks like a really familiar structure, and that's because it's the ester with an extra proton. So now at this point, all we have to do is deprotonate it. We can use another equivalent of our alcohol if we would like. Oh, we're going to go up in the corner, I guess. And that gives us our final product, the ester. So next, we're going to look at the synthesis of amides. And ultimately, they cannot be synthesized directly from a carboxylic acid. It's pretty tricky because carboxylic acids are not particularly reactive. And if you were to add in something like an amide to react with a carboxylic acid in order to accomplish some sort of substitution, all you're going to end up doing is deprotonating and neutralizing your reagent. So in order to get this reaction to work, you have to use some pretty extreme conditions. So we're going to look at some simpler ways to get this done.